Hi everyone, second video for chapter 6 on intermolecular forces and allotropy, and in this video we're going to look at how to determine if a molecule is polar as opposed to last chapter when we looked at if bonds are polar. Okay, so one property of molecules that determines a lot about how their physical and chemical properties is the polarity of that molecule. And the polarity of a molecule is just about how the electrons are distributed. Are they even or uneven? Just like they were in a bond where one atom was more electronegative than the other, so it kind of had more electron density around it, the more electronegative one. Here we can track that through every bond in the molecule to determine if overall in the molecule more electrons are over one side than the other. Okay, when more electrons are over one side than the other, it's called a polar molecule. And here in the picture we've got an example of hydrogen fluoride, where hydrogen here and fluorine here, and in this bond hydrogen is a lot less electronegative than fluorine. Fluorine's the most electronegative. So all the electrons are really kind of heading over to this side of the bond. And there's a lot of electron density around the fluorine and not much around the hydrogen. So in that bond, the fluorine's hogging those electrons. And so in the molecule, because there's only one bond, we've got a polar molecule as well, because all the electrons density is all up this side, not much up this side, just a little bit. Okay, so if it were evenly distributed, so we had fluorine gas with fluorine here and fluorine here, one of the atoms wouldn't have a greater pull than the others, and the electrons will be more evenly distributed. Okay, and so just like when we're talking about the polarity in a bond, it's not definitely it's a polar bond, it's a not polar bond. We tended to call that it was a polar bond if it had electronegativity difference greater than 0.5, but it's more like on a spectrum. So there's molecules that are very slightly polar, there's molecules that are non-polar, and there's molecules that are very polar, and there's a whole spectrum in between there. Okay, some new terminology. A polar molecule is sometimes called a molecular dipole, or just a dipole. And di meaning two and pole meaning pole. It means it's got two poles, a positive and a negative. Okay, you could call it, and it's very similar to a magnet. A magnet is also a dipole. It's got a north and a south pole. So it's also a dipole, and it's very handy when you're thinking about polar molecules to think of them as little magnets that spin around and align to each other. Okay, a very good model in your head. You know how magnets behave. Molecules behave the same way, positive to negative. They will attract each other and align, just like little magnets. And so I put this image in. Water is a polar molecule. I thought that was quite cute. Anyway, okay. So to determine a polar molecule, the first thing you need to know is you have to assign the polarity to each bond. Is each bond in that molecule polar? And we go back to this Pauling scale of electronegativity values. Pauling after Linus Pauling, a very famous chemist, pretty cool guy, dead now, but did a lot of work with chemistry and also did a lot of behind the scenes work on the structure of DNA too. Anyway, but these values, remember, we're finding the difference between them. So is the bond polar between fluorine and hydrogen? Well, we take 3.98 and minus away the 2.20, and we get 1.78 if my maths is correct. And remember, the arbitrary line was if it was greater than 0.5, and it is. So we can say that hydrogen and fluorine, when they're bonding to each other, is a polar bond because the electronegativity difference is greater than this 0.5 value. And so remember, the values increase across and increase up. Notice they haven't got the noble gases in here. So the most electronegativity negative is your fluorine one there. Okay, so first we're deciding, is the bond polar? Okay, so rather than remembering these numbers, because you're not going to and no one's expecting you to, and they don't tend to give them out in exams, what they do tend to kind of assume is that you know some common polar bonds and non-polar bonds. And we'll kind of come back to this during the course. So over the course of 2 years, you'll kind of get to know, kind of go, oh yeah, carbon hydrogen is not polar, oxygen hydrogen is polar, and so you won't need to know these values, you'll just remember these combinations. And there's not too many combinations that you will have to remember anyway. So I've got a table here of common polar bonds and common non-polar bonds. Notice electronegativity difference less than 0.5, greater than 0.5. So common examples of non-polar bonds are the carbon-hydrogen bond. It's approaching that 0.5, but we're saying that between the carbon and the hydrogen, they're kind of evenly sharing those electrons. Notice here I've got X and X, and there's no element named X. Just down here I put in, and it's quite common that X, capital X, is used for symbol in chemistry to denote any of the halogens. So any of these guys, fluorine, chlorine, bromine, iodine, not usually astatine though. It's just a little shorthand because they all kind of behave similar. So if you've got two halogens together, of course there's going to be no electronegativity difference. Any two atoms bonded together covalently, no electronegativity difference. That's why carbon-carbon bond is 0 here. Carbon-sulfur, very, very small. And nitrogen-chlorine, very, very small as well. Okay, let's go over to the common polar bonds. Oxygen and hydrogen, whether it's a single bond or a double bond. How can it be a double bond? That's terrible. Oh, I got to get rid of that. That's embarrassing because hydrogen can't form a double bond. Oxygen to hydrogen, I must have been thinking of this guy. 1.24, okay? Oh, I better go in the notes and fix that up. That's terrible. So quite polar, yeah, definitely well above the 0.5. Nitrogen to hydrogen, quite polar, 0.84. Carbon to nitrogen, we tend to call that on the side of calling that polar, even though it's 0.49. Carbon with any halogen is going to be greater than 0.5. And carbon to oxygen we always call polar as 0.89, whether it's a single or a double bond. And a double bond can form between those two, unlike with hydrogen. Shh, don't tell anyone I did that. So this just goes through what I said. Rather than calculating these differences, we tend to remember what bonds are polar and what is not. Okay, indicating polar covalent bonds in a diagram, we use notations. We use these squiggles here. This little squiggle is a lowercase delta, so a Greek letter. Kind of draw it like that. So it's kind of saying we use it here to denote partial. Partial positive, partial negative. It's kind of saying, well, it's not negatively charged, but it's kind of getting along there. And it's not positively charged, but it's kind of getting along there. It's partially there. So it's kind of saying that there's a lot of electrons around here. There's 2 lone pairs around there. Whereas hydrogen, there's not much electron density there, so it's kind of partially positive. And so we put these symbols around there, and it helps us decide where the electrons are hanging out in these polar bonds. Okay, so sometimes we use the term partial positive, partial negative, or delta positive, delta negative. So water here, we're saying that the oxygen tends to hog the electrons in both of these bonds. Okay, from there, we tend to draw some arrows, which are vectors, if you know what a vector is. That's okay if you don't. We draw an arrow parallel to the bond, and it has the arrowhead and the base. Now the arrowhead always points towards the negative, and the base always points towards the positive. And notice what some great chemist has done. They've put a little, I don't want to rub it out, they've put a little cross across the base to give you a little positive saying, this end goes with the positive. It's very helpful. Okay, and we tend to put, so one for each polar bond in there. Okay, so we've got two polar bonds, so we put two of these in here on our molecule. All right. Once we've assigned any polar bonds and drawn our vectors or our arrows, we have enough information to decide if we have a polar molecule or if the molecule has a dipole moment. So if it's polar or not polar. Okay, so first we put in our partial charges here, and then we put in our bond dipoles, so our arrows. And then we have to resolve those arrows. Okay, now, when resolving those arrows, it's going to be that polar molecules, if the answer is this polar molecule, it's going to have more than one or more polar bonds, just like water does here. And these bonds are either not equal or not opposite. Okay? So here in water, they're equal. Yeah? They're equal in magnitude because the size of these arrows are essentially the electronegativity difference between them. But they're not opposite. And bear with me here because they are mirror images of each other, but technically they're not opposite. They're not opposite facing. There's still some component that's pushing down. Okay, if they were completely opposite, they would look like this. Then they'd be completely opposite. But that plus that equals, there's a little downward push because both of them are pushing down somewhat. Okay, you can think of it like two people pushing in that direction. If two people were pushing directly opposite, there'd be no movement, like up here. But if two people were pushing kind of opposite, but in a forward direction, they'd all fall over this way. There'd be a net force in this direction. So there's a net dipole for this water molecule that's in that direction. Okay, so the easy way to think about it, whether a molecule is polar or not, non-polar molecules, I mean, some of them have no polar bonds. That's nice and easy. Or if there are polar bonds, they are both equal in magnitude, so they have the same electronegativity difference, and they are in exactly the opposite direction, so they cancel each other out. Okay, let's look at some examples of these. I've tried to illustrate each. Okay, let's look at this molecule here. It's called ethane. We'll learn how to call these carbon and hydrogen molecules next year, but this one's called ethane. Here's its structure. It has two carbons and hydrogens all around it. Okay. Ethane is a non-polar molecule as it contains no polar bonds. This is a nice simple one to start off with. There's only the carbon-carbon bond and then 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds. Carbon-carbon bond is non-polar because there's no electronegativity difference between carbon-carbon. Okay, carbon-hydrogen bond is non-polar because the electronegativity difference is less than 0.5. So all the bonds in this molecule are non-polar, so we have a non-polar molecule. So 0 net dipole moment. Okay, next example. Chloromethane has this structure. 1 carbon, 3 hydrogens and a chlorine at one end. Okay, so let's designate the bonds here. The carbon-hydrogen bond is non-polar, and we've discussed why before. It's less than 0.5 in the Pauling scale there. The carbon-chlorine bond is polar because you do the difference and it's 0.61, and that's greater than 0.5. So we've got one polar bond here. So we go, oh, chlorine's more electronegative, so it gets the delta negative, and therefore carbon is the more electropositive, so it gets the delta positive. And then we draw our arrow in, positive base, we draw it in there, okay? Now, we have a polar molecule as it only contains one polar bond. There's no other polar bonds that may be equal or may be opposite here. So we definitely have a polar bond, and there's only one arrow going this way, so that's its molecular polarity as well. So we've got a polar molecule because we've got one polar bond in there. Okay, let's look at an example here of water. We've only got 2 oxygen-hydrogen bonds. Do the electronegativity difference, and we get 1.24. So we've got 2 polar bonds here. Oxygen has the lone pairs of electrons. It's the more electronegative, gets the delta negative. So each hydrogen is a delta positive. So we can draw in our vectors the positive bases towards the delta positives or the partial positives, and the heads towards the partial negative there. Okay, with 2 polar bonds equal in magnitude, so we're fitting the equal in magnitude. But, as I said before, they're not opposite. They're mirror images of each other, but when we add them together, like what I've done down here, they don't end up in the same spot. They're not completely opposite. We get a net dipole moment for the molecule that's just a little bit towards the oxygen there. So the oxygen is delta negative and these are delta positive. So we've got a polar molecule. Water is quite polar. Yeah? Okay, let's look at another example. I've got the molecule ammonia here. Ammonia NH3. Okay, so we've got 3 nitrogen-hydrogen bonds, and each of them is polar because the electronegativity difference is 0.84. Okay, lone pair of electrons on the nitrogen, it's the more electronegative, delta negative, partial negative. So each hydrogen then is a partial positive. Draw in our 3 arrows. Okay. Now we need to decide whether they're equal and opposite. They're equal because they're both between nitrogen and hydrogens. But are they opposite? Well, because of the shape of this molecule, because it's trigonal pyramidal, they're not completely opposite. Okay? The direction that goes in this way and that way and that way all cancel out. But overall, there's a little bit of upwards push there. I'm calling it push, but a little bit of upwards net dipole moment. So we've got a polar molecule because of that pyramidal shape, that upwards dipole moment there. Okay? Add the 3 arrows end to end, and they end up being a little bit up. Carbon dioxide is a non-polar molecule as it contains 2 polar bonds that are equal and opposite. Okay, so here we've got an example of 2 polar bonds, they're equal and opposite. Okay, so oxygen is more electronegative and it has these lone pairs on them, so that's why it's delta negative, partial negative. So therefore the carbon is partial positive. Draw your 2 vectors in. Okay, now they're equal because they're both between carbon and oxygen. They're both 0.89, and they are opposite because add those 2 arrows end to end and you get back to the same spot. So there is 0 net dipole moment. Carbon dioxide has 2 polar bonds in it, but it's not an overall polar molecule. Alright, next example. Carbon tetrachloride. Here's another one that contains polar bonds, but is not polar because they're equal and opposite. It's a bit harder to see here because it's in 3 dimensions. Okay, carbon tetrachloride. Carbon to chlorine 4 times, single bonds. Chlorine has 3 lone pairs, so therefore they're all delta negative. They're all hogging those electrons. The carbon in the middle is delta positive. Okay, draw your 4 arrows in. Okay, they're all equal in magnitude because they're all 0.89 because they're all between carbon and chlorine. Now it's hard to see here, really hard to see, but they are all opposite. Okay, one is not directly opposite to the other, but between the 4 of them, when you add those 4 arrows together in 3-dimensional space, you end up right at the center. So, as I said here, this is really hard to show in 2 dimensions. But because of that tetrahedral shape and they're all equal, they all end up being opposite, and there's 0 net dipole moment for carbon tetrachloride. Okay, so to determine whether a molecule is polar, draw the Lewis structure, determine its shape, we've done those skills, Assign the polar bonds using delta negative, delta positive, and the vectors. Okay. Finally, add the vectors together. Are they equal and opposite? Is it polar or non-polar? Okay. Let's do some examples in real time here. Carbon monoxide. Draw the Lewis dot structure. Okay. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. They're valence electrons. Okay. Put one bond in between. Okay. I would suggest putting another bond in between. So now I've got okay. Oh, why did I choose this example? Okay, 2, 4, 6, 2, 4, 6, 8. Oh, hold on. Why did I choose this example? I'm terrible. I can't even do a Lewis dot structure of carbon monoxide. What am I missing? Would there be... Carbon doesn't really like lone pairs though. 2, 4, 6. And it won't have them singly. Maybe it must be 2, 4, 6, 8. Oh, this is dodgy as anything. I'm just going to check if it's a triple bond with 2 lone pairs, just online. I've given myself the hardest example of all. Really embarrassing. Lewis dot structure, thank you Google. I'm just Googling it here. Carbon monoxide. This is terrible. Oh, this is one example where carbon does have a lone pair. So I got that right. That's terrible though. Okay, so we've got carbon and oxygen with a triple bond and the 2 lone pairs. Okay. So which is more electronegative? The oxygen is. It's further to the right. So it's delta negative, delta positive. And I've already seen back here that the carbon-oxygen bond is polar. I should have told you that from the start. Because it's 0.89, it's greater than 0.5. So we have got a polar bond here. Sorry about all the scrolling. Positive to negative, okay? And we've only got one bond here. So if the one bond in the molecule is polar, the is a polar molecule. Because we don't have an equal and we don't have an opposite, we just have that. So all the electron density is all up around the oxygen and less around the carbon, kind of like that. Alright, hopefully the next one's a bit easier. I'm terrible, aren't I? Okay, so nitrogen dioxide. So we've got nitrogen, oxygen, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, let's start. Oh, let me go back one. That's terrible. Okay, one bond between each. Now this nitrogen in the middle has 2. I would suggest that what would occur... Have I given myself another hard one? Let me draw it. I've given myself another hard one. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Gotta Google it again. Oh, I should really practice these before doing them, shouldn't I? Alright. Oh, no one's giving me... Let me go to images. That's terrible. You're terrible, sir. Okay, it'll do anyway. Okay, so the nitrogen-oxygen bond is polar. And let's check out this shape. Oh, we didn't really talk about... Well, the shape for that one there is linear, of course, because there's only 2. But here, central atom is the nitrogen. How many bonding regions have we got? I've got a lone pair, this bond and this bond. So I've got 3 bonding regions. So it's actually 3 bonding regions with 1 lone pair. So let's redraw the molecule shape. Nitrogen in the middle, lone pair. It's kind of a trigonal planar basis. But it's a bent molecule, so it's 120 degrees between these. Okay, so we've got a bent molecule, two polar bonds, delta negative because of all the electrons, because oxygen is more electronegative than nitrogen on the periodic table. It's 1 to the right, so that's our delta positive. So let's draw our 2 arrows in. Okay, are they equal? Yes, because they're between nitrogen and oxygen. Are they opposite? Well, no. They both add end to end to produce, sorry, excuse me, a net dipole. Excuse me again. That's a bit better. A net dipole in that direction. So we have got a polar molecule. So NO2 is polar. Alright, let's move on to example 3. H2S. Oh, wasn't I talking about this one in the last video? Okay. But that's okay, we can start doing a little start diagram. Sulfur has 1, 2, 3, 4, 5, 6. Hydrogen has 1. Hydrogen has 1. Draw a bond in there. Hydrogen now has its 2. Hydrogen now has its 2. Sulfur now has its 2, 4, 6, 8. Okay. How many bonding regions have we got? 1, 2, 3, 4. So it's a tetrahedral basis. Okay, but it's got 2 lone pairs. So it's actually bent at 109.5 degrees. Okay, so we've got a bent molecule. The sulfur-hydrogen bond is polar. Let's just make sure. Sulfur is 2.58 minus 2.2. Oh, it's not polar. What a terrible example, Mr. Roberts. Anyway, we've got the sulfur-hydrogen bond non-polar. So we don't have any polar bonds in the molecule, so H2S is a non-polar molecule. Okay, example number 4. Difluoromethane. Alright, CH2F2. Carbon in the middle. F. Oh, let's not put a bond in there yet. Carbon, 1, 2, 3, 4. I'm getting ahead of myself because I know what I'm doing. It's terrible. I've got to presume that you guys don't know what you're doing, do you? This is the first time you've done this. 7 valence electrons for fluorine and 1 for hydrogen. Okay, put 1 bond in between. They're sharing 1 electron. Okay, this hydrogen's happy now. It's got 2. This hydrogen's happy now. It's got 2. This fluorine is now got its 8. This fluorine's now got its 8. And this carbon has now got the 4 single bonds. So that's the shape there. There are 4 bonding regions. There's 4 bonds. So it's a tetrahedral shape. Dashed and wedges. Why not? Pull them out. Okay. Have we got any polar bonds here? Well, the carbon-hydrogen bond is non-polar, but the carbon-fluorine bond is polar. The fluorine is much more electronegative, so it gets a delta negative. Delta negative, and the carbon therefore gets a delta positive. So we've got 2 polar bonds, one going into the page, and 1 there. Okay, now, is the molecule itself polar? Are they equal? Yeah, they're equal because they're carbon to fluorine. Are they opposite? Well, no, they're not. They're kind of like water there. They're bent at 190.5 degrees. So overall, there's a net dipole moment of carbon between the carbons there and the fluorine, or the molecule difluoromethane is polar. So it's a polar molecule because they're equal bonds, but they're not opposite. Trying to spell molecule while I'm talking. Terrible. Okay. Hopefully that made sense. Two videos that I've got here. One, a bit of a revision on bond polarity that I found. That was quite good. And this one here, polar and non-polar molecules by the organic chemistry tutor. Maybe they'll explain it in a slightly different way or better way or just in a different voice. Okay, a couple of helpful links. The Libra texts on molecular polarity and another link there for you to check out. Okay, you can go on to that activity and check your understanding. And next video, I'll start talking about intermolecular forces. Okay, building again on yet that early thing of where molecule shape, polarity, that type of thing. Okay, we'll finally get us there. Thanks for listening, guys.